Hello, let's wait a few more minutes until others join us and then we'll start. Oh. Okay, I guess we can start. So, hello everyone, and as I promised on Monday, today we will mostly have a theoretical session about the algorithms, about the theory of the algorithms in general. How do we see them in our code? How we construct the code based on the theory of the algorithms. And yeah, so we will take a look on this presentation today. Then we will this will be something similar to what you had on your practical assignment on the algorithms. So then there you had the linear equation with two variables, and we'll now create then the algorithm which can actually solve the equation for any parameters of the two variable equation, linear equation. So then we will, so once we gone through the theory about the algorithms, we can actually count the time consumption for the algorithms we created before. We'll take a look on some algorithms, mostly on the cycles, and then I guess we'll have time. Then we can take a look on the fourth task of the practical assignments, on the practical assignment for about the arrays. Okay, but before we start, so here you can see, I'll share the list of those who submitted the practical assignments. So then just maybe in case I'll send it under homework help. So I sent the list of those who submitted the tasks. So just in case I missed anyone, then please let me know. So basically, if you submitted the task and it was correct, I mean that everything is done. There may be some minor mistakes, but that's not the problem here. So then this would be 1 point, yeah. So just like if it's done or not done. So you can find in the list I shared in Discord. So just in case I missed anyone, then please let me know. I'll double check. Also, I see that some of you did not share the. If you did not share your Git repository with me, so please do it, because that's necessary for the further tasks. And yeah, so just if anything is missed, then please let me know. Okay, so that's about it, and now we can start with the presentation of the algorithms. Okay, so you already know what the algorithms are. So you know what is the role of the algorithms in programming. So basically everything what we write, all the actions we define, all the steps we define, the flow of the program we define is actually called algorithm. And so the algorithm is executed by the program, actually by a computer, which is written as the language you use. So you write the program, that's the language, C#. Then this language is actually translated to the language that can be understood by computer, and after that then it's executed and you get the result. So just again, small recap. First of all, let's inform the algorithm is a well-defined computational procedure. So and this procedure is based on the any input. Yeah. So here you see input. That does not mean that these are the input values, but these can be any input values and any input actions, basically done by user. Also this can be the data from the database or just any file or something else, and then based on what the program has, what the program receives, it after that provides the output. The output can be not just simply the output in console, it can be for example, the change in the database, it can be the change in the file, it basically can be any action, any possible action done by program, which has some kind of impact, but just any change, any action done by program, this is considered as the output. Yeah, so just in general, the algorithm is the sequence of computational steps that transforms the input into the output. Yeah. So, and yeah, in general, that's a tool for solving a well-specified computational problem. So it means that you want to do something, you want to automatize process, you want to calculate something, or just do any practical actions, then this can be done when you write the program based on the algorithm. Yeah, so for example, you have the algorithm for insertion sort. So you provide the list of integers with the corresponding length n. So n, that's the length, okay, 1, 2, 3, 4, 5, 6, 7, and so on. Then the output will be the sorted list. So that will, yeah, here you can see the list L. That's actually the name of the list. Let's say the name of the array provided, for example, or something similar. In this case, we don't really talk about the actual data types. Just let's take any list L of integers and we name it L. Then, as a result, we get the output, which is the list, which is different list. In fact, this is not the same list provided. No, it's different list. List integers that are provided under list L. So, and yeah, then we can define the steps. Step 1 would be that we keep a sorted list which starts of empty. So by default, that's the empty list. And then we perform the next step, step 3, for each element in the list provided. And we insert the selected element from L into the correct position. Yeah, so that will be quite simple. So we have the error. We can actually implement this algorithm right now. Maybe create the folder for the algorithms. And then I'll create sortation, sorting CS. Then I'll use system then I will create a class. Then I will create the static method. String. And yeah, so now let's implement this algorithm. So let's say that we ask the user to provide the array. So then maybe I will just simply take the code from this class, and then I can basically sort this array. So let's then do it. And what will I do? I will split the logic into different functions, into different methods. Again, that's up to me. If you want, you can. It's up to me, up to you. If you want, you can write the program here inside this main method. But just to split the code into different sections, then I prefer that would be sometimes better approach. Just put your code into different methods. So then let's do it. So that will be public. So here I will do the sort of array. So what does it mean? It means that I will so I will have the integer array. So it means that I will return also the integer array after the sort, and this would be sorting. Yeah, sorting, and then I'll provide the array to be sorted. The array to be sorted, and that would be, as that was said here, array L. Okay. Then we'll return new array, which will be L1. So let's then define this empty array, the array L1. So we already know how many elements this array will have. So, and then this would be the integer. The number of dimensions will be the same as in the array provided. Okay, and now we can sort. So here I will maybe create another function, and this function will be the following one. I will add the element to the array, and just to not confuse you, we'll use reference, but in fact you will see that we can also skip using the reference, because for the for your information, for the arrays we don't need the reference. So just maybe I will start with reference, then I will then show you that we can also skip using reference. Because the arrays are the objects, and for the objects we don't need reference variable, because the objects by themselves, they are the reference. The value of the object variables, for example the arrays, this is the reference itself. But we'll talk about it during the object-oriented programming sessions, and then I guess that will be more clear for you. So then let's maybe start with reference. It doesn't matter at this point. So, and this would be the array, and say the array L1. Then we have add and element. So, and here we will go through all the elements in the array. And yeah, so in this case, there is one thing. There's one thing that according to this algorithm, it says that this array should be empty. But the thing is that integer arrays cannot be empty. So what can we do? Can we do in this case? So first of all, we will definitely need to go through all the elements of the array. That's one thing. So then I will then I will definitely need to use loop here. So it means that I will be less than the length of the array, and I will be incremented. And so here we need to check if the basically initially we can do this way. We can check if the hold on one moment. Of course, we need to provide the element we want to add. Provide element we want to add. So then I say if element is greater than current element we are looking for from the array, then I need to enter it. But yeah, so what's the problem? The problem here is that basically then we need to also switch, not switch, but shift the elements to the left. So that's the problem for the arrays. So that here we talk about the list, but for the arrays this would be a little bit more complicated because we need to do the shifting. So it means that if we add the element to the end, it means that we need to shift all the previous elements. So in this case, we need to do the shifting. We need to do the shifting, and it means that we need to shift all the elements to left. And this would be, I would say, not quite easy. Not quite easy. Hold on now. So this will be checked, and it means that if the current element is greater than the I element, then we should enter the element on the current position. So first of that would be that L1 is Li is element, but this will not be correct because again we need to shift the elements. In this case, shift the elements to right. Yeah. So then we need to do the shifting. So here I will say shift to right, and here I will then define the position from which we want to shift, and then of course we will add the array. So how can we actually shift all the elements, integer elements? We will need to go through the elements of the array, starting at the current position to right. So the current position would be that again we use I, but in this case that would be starting position. And then we again say that I should be less than the length of the array, and then we increment I again. So, and now we need to shift all the elements. For each element I need previous element. So that would be that would be the following thing. So we need to shift them. We need to shift them right. So this means that we will assign the previous element to the next element. No, hold on. Hold on. Yeah. So we need to then. One moment. Let me maybe quickly think. Oh, yeah. So in this case, then we'll check that the element is less than the element that will shift to the right. Okay. So then we'll shift. Yeah, we'll shift to the right. So it means that the next position will be the same as previous. So yeah. So it means that L next one, that's I plus 1, will be the same as L I. No, hold on. So that means no, that would be the opposite one. So the current one, no, the current one should be the previous one. So then we can say that, okay, the position would be one moment, that's let me quickly think. So let's quickly imagine. We have the elements 1, 2, 3, 4, and then I want to shift them right, starting from here. We say we have 5, so we have something like 0 at the end. So what will I do? I will then start at the second position, then I will go to the third position. Oh no, we actually need to start from the end. That's the point. Okay, so then we start from the end, and then we go the opposite direction. Yeah. So in this case, we need to start from the end. Then we will have the situation when the current element will be the same as previous. And so it means that here we go start from here. Then we check the previous element, previous -1. So this will be 4. We go here, then this will be 3. We go here, then this will be 2. Go here, and this will be 1. So that's the way. And yeah, so then we need to go the opposite direction. Then I say that this should be until we reach the starting position, and then we actually then need to decrement. Right? Okay. So that's the thing, and that's the point. Okay. So then, and we say that the current position equals the previous one. And in fact, here we can also skip the brackets. And I guess maybe some issues we'll see. And then here we can do the shifting. So if the current, so for example, let's say that we have such arrays. So initially the arrays, say we have 5 elements. Initially the arrays, integer arrays, contain zeros only. Yeah, so let's say that we want to sort the array. So do we have something like this? So let's, for example, start with different numbers. So let's take the first one. Then we go and check, is 4 less than 0? No. Then it should be entered at the end. So you will go through all the elements, and then we'll go at the end. So then we take 4. Then we go with 6. Again, we say that 6 is not less than all the elements. Then at the last point, we need to shift the elements to left, actually, in this case, yeah. Shift elements to left, and then add element 6. So then we process the element 6. We then go with the element 3. So we see that element 3 is less than 4. So it means that in this case, in this case it should be entered here. Then we go with the element 8. Or maybe let's do it the following way. Let's say we have 5 here. So then we start with element 5. We go through the first. Then here we need to shift all the elements actually to left in this case. So it means that we will start start here, and then we'll move. We actually start from start in this case. So then we'll say that 3 goes here, 4 goes here, and here we'll add a 5. Okay, so then this one is done, and then 7 again should be entered at the end. In this case, we need to shift all the elements to left, and then 7 will be here. So maybe we'll implement this. I will finish this algorithm maybe a little bit later. So just for now, to maybe go back to the theory, we'll finish this a little bit later. For now, let's maybe continue with the presentation, because again, initially this should be handled by lists, and if we when we talk about the list, then this will be handled much more faster, because for the lists it's easy to implement, but we'll finish then this one a little bit later, just for now to focus on the presentation. So let's say then this algorithm is implemented, and so the next one is actually for the arrays. For the arrays, that will also be insert sortation, but in this case, so we should iterate from the first element to the last one, and then compare the actual key to the comparison. So in this case, we have only one element of the only one array, and so actually to sort the array, in this case it's actually not as complicated, because in this case we actually need to swap the elements. So if we talk about the swap algorithm, then it's quite easy. We can implement it. It's much more faster, much more easier. So sorting using swap operation. So in this case, I will use the same term we used here. So I entered the elements, and actually now we can sort. So let's say that we have the key, and then the key will be let's say that the key will be the first element in my array. That would be the first element. So the first element will be the key, and then we need to go through all the elements of the array. So I'll use the simple loop approach, and then I will increment the symbol. So, and here what we need to quickly check, so is the current element of the array is less than key, then we need to swap the elements. So to swap the elements, we can do it quite easy. So in this case, one moment. Oh no, according to the queue, actually can swap the two elements. In my array, I plus 1. Again, yeah, in this case, we don't need a key. So then we will say, so here I'll have this key here. So then I will, so how to swap? So we need one buffer variable in between. So we'll keep, so to keep the value from the previous one, then now we can change the value of this one and then assign the key value here. Oh, hold on, one moment. No, actually it should be the opposite direction. Just want to sort from smaller to larger. Okay, so and in this case, we actually need to go through all the elements. And yeah, so we start with all the elements, but then actually we need to do it a little bit, because yeah, what's the point? The point is that this is actually bubble sort. And so now we can actually implement bubble sort. This would be the way that the largest element will definitely go to the top. So, and from here, oh, hold on, not array length, but it should be less than my array length minus I. So that would be 1 point. And then we can do the swap. But in this case, here we need to use J, and you'll see why. Just a small adjustment. Okay. So, and let's see what's the result now. So now I'll use for each loop to print all the elements. This would be my array. Then I print the element into space. Okay, so let's then do it. Let's run the program. Be sorting swap. Oh, compilation error. We have, oh yeah, of course, need to go under the algorithms folder. And now I can compile the program and then run it. So let's say that I enter some elements. I can also, maybe let's just enter, yes, I can also enter negative elements, but just maybe center them later. Okay. Okay, so here I have the exceptions that the index is out of bounds of array, so it means that I can, okay, then I gone a little bit too far. So, and so it says that the problem comes from which one? Okay, so it's so oh, okay, let's then check. Okay, so here we have j plus 1. Okay, then I got it, j plus 1. Then it means that for the last one we cannot do it. So in this case we need to have minus 1. Minus 1 because for the we have the last element. That's why. So let's recompile the code. Okay, and now we can see that our array is sorted. So actually, yeah, this is the sorting way how we can use how we can do it using swap. So actually, I guess we did not cover swapping before. So right now we can see how to do it. So, and in this case, actually we work with one array only. And what you can see here, this is the bubble sort. This is the bubble sort, so that's the part of practical task 4. So since we just implemented it, let's maybe quickly talk about how this algorithm works and why it is called bubble sort. So basically, the idea is it comes from the name of bubble sort. It means that we have bubble, something that is more heavy, in this case, that is more heavy, that goes to the top. That goes to the top. And this is basically how the algorithm works like. So what we do here, we go through all the elements of the array for the first time. And so in this case, let's then quickly write the example here. So let's say that we have the elements, just any sequence of the elements. And let's say -8, so for example. So then how the algorithm works. So you can see there are 2 for cycles. What do they mean? So this one, the first cycle for I, that goes through all the elements. That makes sense, right? What are these elements? These elements are the starting position. So first one, we start at 0. So this is what is set here. Then we have another cycle. Another cycle, that's the actual cycle where we go through all the elements. Basically, we then check all the elements starting basically from the beginning until this, basically until the end. Minus the last element. So basically, for the first iteration, here we will have the number of iteration -1. No, actually, here for the first time we'll go through all the elements. So first iteration. How will the array look like? So basically, we start with the first element, and then we swap all the elements if needed. So for example, first one, we have this element 3. We check is 3 greater than 54. No, it's not. Then we don't need to swap. Then we go here. So do we need to swap here? Okay, yeah, for the first element we keep it as is. Then we go next. Next one we check is 54 greater than -2. Yes, then we need to swap them. So in this case we'll have -2 and 54. Then we go next. Is 54 greater than 73? No, we don't need to swap. Then it will be like this. Then we go next. Is 73 greater than 18? Yes, it is. Then we need to swap them. So it means that I will swap them, and those will be 18 and 73. Then we go next. We check, is 73 greater than 20? Yes, it is. Then we need to swap them. So again, I will swap them. Then we go to the last element. We check, is -8 greater than, is it less than 73? Yes, it is. Then we need to swap them. So again, I will swap them. So here is the first iteration. Yeah, so we've gone through the first iteration of this one. So basically, what this does, it goes from the first element to the last element and does the swap. So nothing, I guess, from this point for the first iteration. Is it clear or maybe not? So that's the bubble sort. That's the bubble sort, and basically we'll have such 1, 2, 3, 4, 5, actually 6 iterations. So that's the first iteration. What we are sure about after the first iteration. After the first iteration, we already know that. So the first iteration, we always know that the largest element will be positioned at the last position. So that is always true. Because again, since we do the swaps, then it means that the largest element will always go to the top. Yeah? It will always be swapped, and it will then be placed at the last position. So that's why we don't need to sort it. Or I mean, we don't need to touch it anymore. We already know that this is the largest element, right? So we already know. Then we go to the second iteration. So, and as you can see at the second iteration, so here we have -I. It means that we don't touch the last element. So it means that the second iteration will be in this case -1. So we don't need to process the last iteration or the last element. So then we need to repeat the same iteration, but only with these elements, because again, we don't need to touch 73. We already know that this is the largest one. Yeah, so we only need to touch now these elements. So basically then we do the same as we did here, but only with these elements. The last element, we can actually, if you want, we can also check the last element, but you will never swap it because that's the last element and it's the largest one. And so in theory, if you do it like this will also be correct. But so here we will do some operations we don't need. Oh, -1 of course. -1 because due to the swap, we check the last element, and that's just a technical thing. Yeah, so that will also be correct, but just too much operations we don't need. So in this case, how we'll proceed? Then again, we'll check is 3 greater than -2. Yes, it is. Then we need to swap them. 3, and then we have -2. Then we check here, is 3 greater than 54? No, then we don't need to swap. We go next, is 18 less than 54? Yes, this, then we need to swap them. Then we go next. To check is 20 less than 54? Yes, it is. Need to swap. Then check next is minus 8 less than 54? Yes, it is. Then we go here. So that's the second iteration. What do we know after the second iteration? After the second iteration, we know that the last two elements are sorted correctly and they are the largest one. That's two largest elements with position that lost two positions. Yeah. So that's what we know after the second iteration. We did the swap with these elements, and now we basically pushed the largest element of these six elements to the top. And this is what we basically can achieve using the swap. So right now we know that these two elements are the largest, and again we don't need to touch them right now anymore. Okay, so then we basically proceed with the remaining iterations the same way. So again, now we don't need to touch these two because they are the largest one we know. Then we need to check these 5 elements. So, and again we proceed this way. Minus 1 is less than 3, so no need to swap. 3 is less than 18, so no need to swap. 18 is less than 20, again no need to swap, but minus 8 is less than 20, so here we need to do the swap. And again, in this case, we know that we have 3 largest elements of the array positioned at the last 3 positions here. And so in this case, we know that these are 3 largest sorted elements. Right? So then the remaining part was these 4. So we can go next. Go next. Oh, sorry. I accidentally tapped on the power button. Okay, that should be better. So here we have the 4th iteration. And then, again, at this point, we know that these elements, we don't need to touch them. Only these 4 needed to be touched. So again, so for these 2, we don't need to swap. For these 2, don't need to swap. For these 2, we do need to swap. So then I'll do it. And here we have minus 8. So at this point, we know that these 4 elements are the largest ones and they are sorted. So this is done. Then we go to the next iteration. We almost finished. So here again we have minus 2. Don't need to swap with 3. Then we have 3 and minus 8. Need to swap them. So we have 3. We have minus 8. So now we know that the last 5 elements, these 5 are the largest ones and they are sorted. So and then the last iteration, 6th iteration, we need to basically check just simply the first 2 elements, and we know that we need to swap them. So we have minus 2 and minus 8. So now the array is sorted. Oh, after the second. Let's then change this thing as well. So that will be 4th. We know that all the elements elements will be sorted. Yeah, so that's basically how the bubble sorting works. Right, so maybe I'll push then these changes to the Git repository just in case you want to take a look on them now. Push the changes. Yeah, so that's basically how the bubble sort works. And it is based on swaps. Okay, so do you have any questions about this algorithm? We'll have a little bit more analysis on this algorithm. We'll see what are the advantages and disadvantages of this algorithm. But yeah, so any questions, then please let me know. So that's the practical thing. Again, on practice, as I said, mostly you will have the methods you can reuse. In this case, we want to, on practice, you may have to implement the different algorithms. For example, the way how you read the entries, how you get the entries based on the data from where you want to get the entries, or maybe also, yeah, get the entries, read the entries, insert the entries, and sometimes you may need to think about the algorithms, the efficient algorithms you can apply. So basically, bubble sort, that can be the start from to analyze the algorithms you can create. And that's the base example for, and I guess bubble sort, that's most simple example for the algorithms. Yeah, so the question here, so there will always be one iteration less than the number of the elements. Yeah, this will always be, but the idea is that, yeah, because again, we have, yes, because in fact, that's a good point, because at the last iteration, you may see that what will we have? Well, we have that I is the length of the array -1. So that would be the length of the array -1. So this would be my array -1 to +1. So that will be 0. Yeah. So the last iteration, when I is the length of the array -1, so it means that this would be like this. Hang on. Array. That would be -1. Yeah, that would be the last one here, because again, I is always less than my array 1, so it means that the last iteration from this loop will be that I is my array length -1, right? Because it cannot be greater. It should be less. This will have -1, and here we have -1. So again, this means that this is 0. So that will be the last iteration. So it means that for the last element, this for loop will not be triggered, and this is because basically for the last element we don't need to swap. Yeah, because at this point we'll already. So it means that if we check all these elements, we do the swap with them. So all the elements -1. Then actually for the last one, we don't need to go through, because again, at this point, we know that all these. So if we know, if we know that all the, like in this case, all the 6 elements are the greatest and they are sorted, so there's nothing left, that the last element on the left is the is the smallest one. So that's pretty much makes sense, I guess. So just from this point of view. And one more thing, how can we actually sort? Maybe the question to you: how can we? What one thing we need to change to actually sort this array in descending way? Just to implement the logic to sort the array in descending way. Oh, actually, yeah. So what we need to do? So just any ideas? How can we adjust this algorithm to sort descending order? Just one small change needed, actually. So if we know that the bubble sort works in the way that we swap the elements, that we push the largest element to the top. So in this case, to sort in descending order, we just need to do the simple thing. We need to push the smallest element to the top. Yeah. So that's just one difference. And what can we do? We actually need to change the sign here. So in this case, we swap the elements in case the element on the right is greater than the element on the left. And so we can then compile the code and run the program. So exe, let's enter some elements. Yeah, so in this case, the sorting will be in descending order, because in this case, it will push the smallest element to the top. So that's just one of the only difference. Maybe I can also comment it here. Change to sort in descending order. So that's just the algorithm to think about. So yes, I had the issues pushing it. Maybe let me try again. Okay. Try again. So that would be 21. So that's part 2. And let's push the changes. So we need to log in. Let me do it. Okay. Okay, then this is the. Okay, there's brownout. Okay, then I'll check because there may be some issues with GitHub. I'll double check them a little bit later. But yeah, that's the bubble sort. I'll push the changes a little bit later then. So, do you have any questions about the bubble sort? So that's the algorithm, basically the easiest sorting algorithm, the most simple one. We'll see that it's not so effective in some cases, but that's the thing to start with. That's definitely thing to start with. Okay, then see, there was the question about the homework help. Oh no, there was not a question. Okay, that's fine. Okay, just in case you have any questions, then now we can have the break, and during the break you can let me know if you have any questions. So let's Start right now. Okay, so let's continue. Yeah, one thing about Git. Let me just quickly, before we continue, let me try again to push the changes. Let's see if it works now. Okay, then let me maybe do it from Git bash. One moment. One moment. It's interesting. Ah, okay. So one thing. Let me try then this thing. Okay, then maybe I'll check it later. Yeah, so there's some issues with the tokens. I will explain to you during the next session, just so for you may also see such issues for GitHub. Regarding the question, in this example, the program asks to enter a number even in the end. Then it already shows the result. So you mean, hold on. You mean, maybe enter again. Manual. So we have sorting swap .exe. Oh, hold on. We need to go next. This would be algorithms. Sorting swap.exe. So then let's enter some numbers. As you ask, enter a number even in the end. You mean right here? Basically, we don't really need to enter a number. We just simply press anything else but integer to close the program. I mean to finish the program, basically to stop the input. Not really sure. We can make it maybe differently. We can also ask user to enter something different. We can also print here that this is the sorted array. For example, this would look like this. So that one sorted array. Just type something. So I mean the last comment right here. Right here we don't really enter anything. But not really sure how. Maybe you have a different idea. What should we do here? I mean, just from the usage point of view, we can basically do whatever we want in this case. But for now, I guess this is the most simple way to determine to finish. We can also say press or press space to finish the input, for example. So then we can check So then we can check that that we have space here. So for example, that would be um, actually we can read the line separately. So right here, that would be string input content. Then we can read something like this. Then we can check if input content say equals space, then we break the program. So we can do like this. Here we can print error message, for example, and then continue if something else is entered and it is not correct. So let's say incorrect input. So then we can do this way. So then, so hold on. Oh no, sorry, here we don't have, one thing. Here we have input content. So in this case, we will provide the input here. This will be stored as string. That's correct. But then it won't. Then it will be used. So just we enter the content here. It will be stored in the program. The program then can use it. But it will read then the input from the separate variable. Sorting. First need to switch to the right directory and then compile and execute. See, so let's enter something. So then if we enter something incorrect, then it will say that the input is incorrect. Need to enter more. Again, it says incorrect, and we can enter more. We can enter more, and then we can press the space and enter, and then it will finish the output. Or just space, or press enter, or press just say enter. Finish the input. Then we can check that the input is just nothing. If input is nothing, then we can close the program. So that would be also the option. We can play around. We can make multiple combinations. That's up to you, to us, and also up to you. But if you want to make something different here, then it's fine. But it's not. I mean, non steps here are mandatory, just as we want. So the approach we like better. So just as well. Okay, so let's go back to the presentation. And this will be how the sorting algorithm, just bubble sort, works. And yeah, so the thing about pseudocode. So during the previous sessions about the algorithms, I mentioned such thing like pseudocode. And sometimes, so this may be not so really clear what the pseudocode is. And the thing is simple. The pseudocode, just to make it maybe more more clear. So normally we don't write the actual codes on the papers. Yeah, so just in case you want to write the code not in the IDE, so just on paper or in Notepad or just as the text somewhere, then we actually never write the code without the IDs. Yeah, but let's say that you want to illustrate your algorithm, and using words, that would be fine. So you describe all the steps, that would be the option. But as you may understand, to transform the code, not to transform the algorithm from the text to the program code is it's not maybe quite complicated, but sometimes it requires some thinking. What are the variables needed? What are the data structures needed? Like that's the array, or basically how can we, for example, we say swap, but how can we actually swap? We say the yeah, I mean we can describe the algorithm in words, but from the programming point of view, we still need to make the adjustments, create the just basically define a different way to then actually transform it to the actual code. And so the solution for this may be Zeta code, which is actually not the program, and it's not the text. That's something in between. So that means that we actually write the program using the text. This is not, from the syntax point of view, this is not correct algorithm, but from the illustration point of view, this is correct. So basically, we create the type of code to illustrate the algorithm. What are the advantages? We'll see the advantages a little bit later. So using the pseudo code, we can actually determine the speed of the algorithm, if the algorithm is efficient or not. If we can do some adjustments in the algorithm, so using the words that maybe will not be so easy, but using the pseudocode, I would say that would be quite easy to make the adjustments to go through the logic, and then that would be quite simple to write the actual program code after that. And yeah, you can see how this will look like. So you can see that from the syntax point of view, that's not really correct. But if we read it, we can really understand. So we can simply understand. So for this case, we say that we have the cycle. We go through all the elements. So in sequential elements, starting at 1 to the actual end of that's the array. And so if we have one to something, usually this is the array, then we can see that we assign the element I of the array A to the X, then we assign the value of I to J, then we do while cycle, we loop through, not we loop through, but we have the iterations while J is less than 0 and the element j minus 1 of the array is greater than x. So while this condition is true, we then do these two steps. So here we assign the previous element to the next one, and then we actually swap the previous iterative with a previous element with the no, the next element with the previous one. So and at the end we actually assign the element x to the array j, to the element j of the array a. So yeah, so I guess that would be simple to actually write such program. I mean real program, because we have the array, we have the variables, we can simply define them in the actual algorithm and then implement them. And so that will actually be the bubble sort. Yeah, we'll swap. Yeah, oh no, sorry, this will be the bubble algorithm and bubble sorting algorithm, and this will be insertion one. You can then check it. But yeah, so that's how we can write pseudocode. So just describe it, and so yeah, this is how this would look like, just from the book again, just word by word, and describe the steps, and yeah, this would look like the program, but not actually the program. So we can also see illustrations. Yeah, so in this case, we can also do loop invariant. Excuse me. So, and this is how this would look like. So, yeah, so just go in opposite direction. So we have this inner loop, how it looks like, and yeah. So now the point is what in this session I wanted to point out is the analyzing time. So basically, what the time means from the algorithm point of view. And yeah, this is what's this session. What's the key thing of this session? For each algorithm we develop, especially if it is related to some kind of calculations. So, for example, sorting can also be considered as the calculation. So we want to determine if the algorithm we're looking for is faster than any other algorithm. And basically, what do we do? What basically the time means? Time actually means how many checks do we actually do? It checks how many elements do we go through. So how many elements we check, how many elements we actually go through. So from this point of view, let's quickly check how many actions we have here. So time, let's calculate. So here we go through all the elements. What does it mean? It means that here we have at least I cycles. So we go through I times, or not I times, but length, my RL length times. So we have the cycle. The cycle is we don't break the cycle at any point, so the time will be, so number of the steps will be at least the length. But for each, you can see that for each iteration from here, we have another cycle. So, and how many steps do we have here? Here we actually have basically, yeah, for each we have viral length minus I. So that would be my RL length minus 1 for the first one. Then this will be my RL length minus 2 plus my RL length minus 3, and so on until we have the last element, which will be 0 actually. So that's the actual time. That's the actual time we can calculate. Yeah. So for each iteration, So we have first iteration, we have the second iteration. This is considered here. And the length, the actual, not the length, but the actual time for each iteration from here is this one. That is different for each loop. If we do it like this, I mean, if we skip minus I, if we go through again through all the elements, we don't need it. This would be, then in this case, the time would be simply my length minus I minus 1 times my array length. Yeah, in case we don't use minus I. Why? Because for each iteration from this cycle, this will be triggered by array length times. Then for each iteration, here we have my array length minus 1 iteration. So it means in total we'll have such a number of iterations, which is no, actually, yeah, again, here we can add more checks. Yeah, so in this case that would be, let's say, times 3. But later on, from the theory point of view, we'll see that we don't, when we talk about the algorithms, we don't really we don't really look on the constant values. Like 3, that's the constant value, so we do not really take it in account. Yeah, so for such approach, this would be that we have this time. But again, let's maybe go back to our initial version. And in this case, the value will be this one. Yeah, and basically, what can we do in this case? In this case, we can do some analysis. What do we know about this one? We know that here we have less iteration than if we had this approach, this variant. And what can we do? We can say that this is actually less than the. This is actually less than. This is actually less than this time. Just. So that's how we can evaluate it. And so that's the analysis. That makes sense, yeah, because if we go through more elements, then we need to have more iterations. And again, just to be more precise, here we can add that we multiplied by 3, but you'll see that we don't really take into account this one. So again, this would be if we multiply it by 3. Yeah, again, the first loop, then the second loop. That's less. That's that the actual value is less because again, here we have less iterations than my array length. Okay, that's why we can do such comparison, and then we see that that's greater. Then what we can do next here. Next we can see that this is less than my array, just time my array in power of 2, just squared. Because again, if we multiply by the value which is minus 1, of course that would be less than if we multiply by the value which is actually plus 1 what we have here. That means that my array length is power 10 square 2. Yeah, so basically this is how we can analyze the time, and later on we'll see that we actually analyze our algorithms. In fact, yeah, this means that we have some constant. Yeah, so C, that's the value, that's the constant. And just the constant value times my array length in power of 2. Yeah, so that is how we can analyze our algorithm. And in fact, you also see that we don't use constants, so we take into account only this thing. Only this thing, we see that the length is actually fixed value. I mean, not fixed value, that's the value we don't know at this point, because this will be taken from the user input. So at this point, this would be the value we don't know. We know what's the value for this one, for constant, that's 3. And so we know this value, but the problem is that we have one value which we don't know. And basically, the analysis of the time needed for this algorithm is based on this length. Yeah, and we usually, maybe I will annotate it like this. Usually it means that this will be constant times n in power of 2. Yeah, so when you see the theory about the algorithms and the analysis of the algorithms, then usually variable n is used. Again, maybe that's complicated for you. Don't worry. That's just if you don't understand such theory, don't worry. That's not mandatory. That's just an additional information which may help you when you actually build the algorithms in future. So that's not something mandatory. If at this point you don't understand, that's absolutely fine. But when you program a lot, so time by time, you not may need to think about, but you will be able to understand such things, and then this will be more clear for you. Yeah. So right now that's just an introduction to such theory. Yeah, so at the end we have such thing. So we have constant value times the variable which is based on the length of the array, and it is squared. Yeah. So that's the time analysis. Yeah. So that is what we're thinking about. How much operations does it take to perform such sorting? And basically, again, everything is based on the user input. So in case we have more elements, then we need to do more operations. That's fine. That's how it always happens. We cannot really know the structure of the array to be provided. If it is maybe sorted, then we don't need to do any swaps. So in this case, we don't need to do any swaps. So we then need to do less operations in such case if the array is provided which is already sorted. Yeah, so, or the worst case may be that the array is sorted the opposite direction, and then we need to do for all the steps we need to do the swaps. So in this case, that would be the worst case provided. So in theory, we don't know. In theory, we don't know what will be provided, and yeah, actually, here you can see that the big O notation is used. So what does the big O notation means? We'll maybe talk about it a little bit later, but actually for the time analysis, you will usually see this big O notation. And actually, this is what for our algorithm. So you see here that we come to the conclusion that our time is less than constant times n squared in power of 2. And yeah, this is also what is said here. That's n in power of 2 again. when we talk about the time analysis, we skip multiplications. We have constant multiplied by some just any variable. Then in this case we skip constant and we get such time such time value, which is called big O from n in power of 2. We'll see later what does it mean. Yeah, so there are also the average case and the worst and best cases. So in this case, we just simply take mostly worst case as the analysis. So basically not the worst case, but we are sure that this is the time our array will be sorted. Yeah, so here you can see the sorting steps. That's basically what that's something similar to what I shown to you before. So here you can see some examples. Basically, I want another example. That's also something similar from what similar to what I shown you before. And the second thing, which is actually the thing which is also important, but not as important as we usually think about the time analysis. That's the memory analysis, because sometimes that may be quite crucial not to spend less memory. So in this case, yeah, let's also take a look how much memory is necessary to perform the insertion sort algorithm we talk about. So in this case, it requires a constant amount of memory, because actually we have the fixed number of the variables we define. And so we have the array. There is no need for the memory there. But then to make the swap, we actually need to make the swaps. We actually need one variable to store the buffer value. I put it here, and it is actually one variable. So that's one. So here we have only one variable we need. Yeah, okay. Actually, we also need the variables for j and I. So that also means that we have three variables here, but that's the constant value. So that's not the value which is based on user input, or which may change, maybe change at some point. That's the fixed value which won't be changed at any point. And that's why we say that that's all big O from 1. Yeah. So yeah, from time perspective, the worst case would be that the algorithm is sorted in the opposite direction. The best case would be that the algorithm is sorted in the right direction we want to sort, and the average performance would be, so that's the thing that we usually take something in the middle between the worst and the best case. So it means that I actually have let's say the array sorted in half, but I guess so. Yeah, maybe at this point I cannot really say what will be the average case, but that actually means that we have the number of iterations in the middle. Okay, and basically, yeah. So how many comparisons will we have for the worst case? In worst case, we actually need to compare, not comparison, yeah, comparisons. For the number of comparisons, this will always be the same in the worst case, in best case, and average case. Why? Because so this is basically the comparison. So you can see that this will this will be the same for all the types of arrays. The only thing again here is the length of the array. Yeah, so for all the other parameters, we don't care about the content of the array. We don't care about the sequence of the element. This comparison will always be in place. Yeah, because again, but the program does not know if the array is already sorted or it's not sorted. The program checks everything. The program needs to check all the elements, and that's why this will be executed in any way. Yeah, so in this case, the number of comparisons will be n squared. Yeah. So the only difference is how many swaps will be there, and so this in the best case we have 0 swaps. In the worst case, we actually need to do the swap on all the iterations. So this will be so basically we'll have swaps at all the iterations here in the worst case. Yeah, so it actually means that the array is sorted the opposite direction. So it means that we'll start from, let's say, that we go the opposite direction. So it means that we need to swap these two elements, and again, basically we need to push 73 to the left. Like in this case, that would be that we need to swap them. Then it was 54, then swap it with 20, and with all the elements, and then it will be placed on top. I mean, in this case, the left. So then we're going to start with 54. That we'll need to actually swap it with all the elements. So that will be the worst case for swaps. So, and the average performance is actually, basically how to calculate the average performance. And average performance can be calculated in the way that it takes all the possible cases and then actually calculate the mean, the average of all such cases. Maybe at this point we won't do it. And okay, so maybe since we already use the time complexity, what the time complexity means? Yeah, we use big O notation. So what does big O notation means? From the, I can just not write here. I can show the definition. So yes, I can quickly take the formula from Wikipedia. That would be just faster. So basically, at first point, we should understand that when we talk about time, the time complexity of basically the time we need to spend to do our algorithm, that's actually the function, yeah, because that's some kind of function from the array itself. But yeah, we usually think about the number of the elements in the array. So that's the function, just any function from the number of the elements of the array. We don't know what this function is. We don't know how to actually. We don't know exact time because for different array structure this may be different. But we know the approximate, how to approximately estimate the time and approximately estimate the function. So in this case, for big O notation, we need the functions. We need the functions, and basically big O notation means that we compare functions. So what does it mean? It means that for large n numbers, because we usually, if we talk about the algorithms, it means that we talk about large numbers. So let's take big O notation from n squared. So like in this case, I can say that this means this is big O notation from from n squared. So this means that's the big O notation. This big O notation from n squared. So this means that just from the theory point of view, there exists such number n starting which all the n's which are greater than this n value. So it means that there exists such number, we can say n0. That's the number that for each n which is greater than this number, the actual function, means that here we are, means that the time for each number n which is greater than the number n0, time will be less than just any constant value. We don't know this constant value, just there exists such constant value that is multiplied by square. Yeah, so that's basically from the theory thing, and this is what we can see here. We can see here that basically for any n numbers, for any number, our algorithm is less than this one, than any constant, than the constant 3 multiplied by I array length in power of 2. And this is what this big O notation is about. We can say that we can estimate the time, and the time would be quadratic square time. Yeah, so, and this is what we usually think about. If this is the linear time means that this is just simply big O from n. It means that there is no multiplication, so basically non-factorials, non-square roots, just the linear time. Yeah. So in this case, that would be that the time is less than, if this is just simple n, like we have here, it means that the time is, let's say, approximately just any constant value times n. So the time, say, is less than, so just roughly say, if we roughly say that this means big O from n means that time is less than just the constant value. We don't know this constant value, it can be any value, and multiplied by n. So that's the linear time. That's the linear time. And yeah, in fact, there can also, yeah, we can say that. We can also add maybe some more constants, but we do not take into account them, just the multiple. We are only interested in multiplication. And so that's the actual estimation of the time. Yeah, so big O from n means that the time is, we roughly say that the time is less than the constant. And again, n is the number of the elements in the array. Yeah, so that's the length of the array in our case. And the same as for O from 1. It means that this is the it means that the time is less than just one constant value. We don't know what the value is, but in this case we know the value. I mean, for our case, this is the value 3. But usually, again, we don't talk about the constant values. We just simply say that this is constant, and then we simply define a constant using the big O from 1. Yeah, because it means that the constant is multiplied by 1. like previous we multiplied by n, here we can multiply by 1, and that's why we say that that's big O from 1. So the same is for all the other functions. Like here we have n, we can also have n squared and the square root of n, the cubic root of n, just n in cube, and so on. We can have factorial, and for such cases, then you also see big O notations. So, and that is what we use to estimate the time of the algorithms. And actually, there is one thing what is needed, what may be needed when we do such analysis. That is, I will quickly find comparisons. It's, I guess, firstly, it's obviously done that big O from n time is faster than big O from n in power of 2, right? Because that takes less steps. That's quite obvious. Then what we can see, okay, here we have this picture. So we can see that n in power of n, that's the worst case, the worst function, because n in power of m, it's usually bigger value than n in power, not usually, but that's let's say, yeah, that's usually bigger value than n in power of 2, than n in power of 3. So that makes sense, because n in power of n, that's quite large value. Then we can see that n in power of 2 value is less than n in power of 3. And the same we can say that n in power of 5 will be greater than n in power of 3, because that makes sense, right? And that determines the speed of the algorithm. So if we have the function which is, like in this case, we can see that it increases slower. Like we can see that this function n in power of n, it increases quite fast. Then we can see the other functions that increase not so fast, that increase slower. Then we have linear time, which is O in power of big O from n, and that means that's still simple linear time. And then we have logarithmical time, which is better. I mean, if we look on the big n numbers, large n numbers, these are the numbers we usually think about, and then this is better than linear time. That means that the time is it takes less steps, so the time is better. And then the constant one is just a simple constant time, O from 1, and of course that's also better than the logarithmical time. Right. So I will then copy this picture. So just for you to know. Right. So basically, these are the functions which we usually take a look on to compare our algorithms. I mean, yeah, at first steps, this is not important for you. So for now, you just simply learn how to make the algorithms. But I mean, when you get some experience in programming, when you work with the databases, when you work with the data, so I mean that you should think about when you have collections with tens of thousands of entries, for example, then you need to process them, you need to make insertions, then you maybe need to sort them or read from them. In this case, to make better algorithms, to understand the sequence of the operation. So for this case, that would be let's say that you want to insert, let's say just you simply have the list. Okay, we have not talked about the list, but I guess you understand that the list means that this is the list of integers. Let's say all the integers, or just any variables. So let's say that you have the list of integers, and so the question maybe what should you do first? You should insert the element, or you should first sort the list, and then after that to insert the element. So that may be quite that depends on what are your needs, because so for example, if you want to, so that would be one of the next steps we have. But let's say that you have the list and you want to read the values from it. Again, when you simply have unsorted list with the values, then in this case, the only way how to search for the element is that you need to go through all the elements. And in worst case, you will go through all the elements. And so let's say you have the list of 10 elements, then in worst case, you will need to do 10 steps to search for the element you are looking for. Again, if this is the database, for example. Yeah, so maybe I can also quickly show it in Excel. Just let's have 5 names. Maybe quickly write the name. So let's say that this would be just some names. Just some random names. And just something like this. So let's say that this is kind of database, or just some entries on the database, and so you have the request to search for the, let's say that you need to search for, say, Christoph vehicle, for example. Then, so in the just when we have simple data, we need to go through all the elements. So in the worst case, Christoph vehicle will be placed on the last position, and this means that we need to do 5 steps. So the time complexity would be, let's say, search for any person. This the time complexity will be O from n. So in this case, that would be O from 5. But I mean, if we have the database with the more elements, then the time complexity will also be O from n, but n will be different. Yeah. So that's if we search for the person. We have unsorted list. But let's say that the list will be sorted. Hold on. Say that we know that the list is sorted by, let's say, by name, for example. By name and then by surname. So I can sort it. Let's say custom sort. Then I will sort by column. Okay. Sort by column A. Yeah, so in this case, the list is sorted. And actually, how can I sort now? So previously I just simply had to go through all the elements. But in this case, I know that the array is sorted, or the array, the entries are sorted. So basically, I can do it in more smarter way than I did here, because I know that the entries are sorted. So in this case, I can do such thing like it's called binary search. Binary search, what does it mean? It means that, for example, I'm searching for, let's say again, Kristaps, no, maybe not Kristaps Weep, but let's say that I'm searching for Ernest Wiedeker, for example. So what can I do? I can again, I can divide this list in two. So I go to the middle element. So I know that the size is 5. So I go to the middle element. So I split it in two parts, and I go to the middle element. I go to the middle element. This element is Kristaps Weep. So the name is Kristaps. So I know that I'm searching for Ernest Wiedeker, and the name Ernest is actually, from the sorting point of view, it's smaller than Kristaps. So in this case, I don't need to check these elements, which are under Kristaps Weep. So in this case, I know that I only need to search these elements. Yeah, and for all the databases, for all such cases, if that's the array, the list, then the number of the searches will, so at the second iteration. So the first iteration is simply we take the middle one, then we compare the element we are looking for with the middle element, and then if it is less than the element we are looking for, then means that we need to go down. If it is greater than the element, oh no, sorry, if it's less, if it's greater than the element we are looking for, then we need to go up. And in this case, the number of the checks is reduced by 2. Yeah. So again, in this case, I don't need to check these elements for the sorted array. For the sorted, again, we can say the array with the database table. We can say that we don't need to search. Search, but we don't need to check these elements because we know that this is sorted, and we know that it's then the element we're looking for will not be here because we have sorted the list. So we definitely know that Ernest will be on the top of Kristaps. Yeah, so then I go and check these two elements. And again, here I can check middle element. Since we don't have middle element here, then I can take middle plus 1. So that will be this one. And here I check is Ernest greater than Yanis? No, it's not. It's less. Then again, I go to the top, and here I have found for the entry I'm looking for. So in this case, I spend less operations, and the time complexity would be search for any person. In this case, the time complexity would be actually the logarithmical time from n. So in this case, that would be logarithmical time. Actually, I can prove why it's logarithmical, but in this case, that's maybe not so important for the proof. In this case, we simply know that logarithmical time is less than n. So in this case, the searching will be faster, because this is we have sorting algorithm. So in this case, as you see in here, I use this advantage of sorted collection, sorted lists, to then apply faster algorithm to then search for the entry I'm looking for. But what's the problem? The problem is that this algorithm cannot be applied to, so the algorithm I just talked about here, I cannot apply it to unsorted list. Why? Because this logic simply will not work. Yeah, if I split in 2, then so I can go to the wrong direction. Yeah, so for the arrays the lists which are unsorted, I can only check all the elements. Yeah, and so basically that's the motivation we can really talk about when, that's one of the motivations But actually, from my experience, also the search for the elements and inserting the elements, that can be different for sorted and unsorted lists or the arrays or whatever data structures we talk about. So that was one of the examples, but here we can see that based on the data structure, the algorithm maybe we can find faster algorithm. Okay, so from the theory, I guess we can, finish the theory part because we actually covered the main steps, and then after that, after the break, then we can do some practical things from the agenda. But yeah, so let's have 10 minutes break. In case you have any questions, please don't let me know. Okay, so let's move on and yeah, as I promised, let's create one small solution, basically how to solve the linear equations using the basically any linear equations with two rows based on the parameters provided. Yeah, so that was similar as you had in your practical assignment about the algorithms. So let's then implement it here. Okay, so let's then create, and then will be here equation solver s copy paste the first steps. We have sort and swap, maybe just, and yeah, here let's create the linear equation solver class. Main size, and then the argument, the array of strings to be passed as the argument, and then same row, and to open close the method. Yeah, so first of all, let's ask user to input the first input the value. So again, how the linear equation looks like. So we have the first row. So that will be, let's say, coefficient a11 times x plus a12. That's again the value times x that equals to some value. Let's say c1. Call c1. So then the second one will be a21 times x plus a22 times y, where's not x, times y equals c2. So then we need to solve such equations if we know the parameters, these 6 parameters, yeah, a11, a12, c1, c2, a21, and a22. So then we need to ask the user to provide these parameters. So let's ask user, please enter, so this case we'll say parameter a11. And then we can use this while true approach. So we ask user to provide correct input. So we can enter any double values. So in this case we say 2. Oh, of course we need to declare divisibles. So let's declare divisibles. Int a11, ai2, a22, a21, c1, and c2. So, and here I write the logic. So that would be, we'll parse double. Oh, sorry, not int, but double first, because just in general case we can have. Here you can also have complex numbers, but let's maybe not take into account complex numbers, so just simply all the real numbers we can enter. Yeah, actually, just for information, like mathematical point of view, we cannot enter all the real numbers, only the decimal numbers. So they have limited number of decimal places. For example, we cannot write the value of square root, so only rational numbers. We cannot write irrational numbers like square root of 2, square root of 3, like e value, pi value, p value. We cannot store them physically in, the raw value, because the value has endless number of decimal places. But that's just a small fact. So in theory, we work with rational numbers only. So these will be doubles. Then we say parse, try parse as always, and then I will ask user to provide the input, and then this would be say a11, a11. So and then if it's true, then I break the loop. Otherwise, I say that input is not correct. Input is not correct. So that's the thing, and then we can actually repeat this for other parameters, but again, to not just simply copy paste. Again, what we can do, we can create the function, the method, where we can do all these things. And then let's say the function name would be enter parameter. So here we can say enter the parameter we want to fill, and then parameter name of string parameter name. Then I can copy paste the code there. Then I can parameter name here. And yeah, so one thing here, we definitely need to use reference. We definitely need to use reference to actually fill the parameter. So and here this will so not parameter name, but parameter. Because otherwise the value will not be changed. So then I will ask user to enter the parameter. So that will be for a11. I'll say that that's a11, and then the same for the other parameters. A21, A22, and A12. Okay, but just follow the sequence. Let's do it in this way. Okay. So and then also the parameters for C1 and C2. So okay, now all the values will be entered, and now we need to calculate basically to find x and y. So how can we do it? We can use the determinant approach, and this would be the following way. So first of all, calculate determinant. And so to calculate determinant, this would be quite simple. I have determinant of a11, a12, a21, and a22. So then I simply say that that's a11 times a22 minus the multiplication of A21 and A12. That's that point. And there's one rule. Not all the linear equations can be solved. So if determinant is 0, then it means there's no solutions. So basically it means that the lines are linearly dependent. So it means that I have one line which is not basically needed. So for example, that would be just one simple example. I have such equation like, let's say 2x plus, let's say 7, y equals 9. That's the first equation. Then I have the second equation, let's say 4x plus 14, y equals 18. So basically you can see that I just simply multiplied this row by 2. So, but in fact, I have, so this does not give me any information, right? Because I simply can divide this by 2 and I'll get the first equation. So in this case, the second equation does not provide more information about x and y. So, because in fact we can modify the equations by multiplying them or dividing them, and they will remain correct, right? So in this case, we can see that determinant will be 2 times 14 minus 4 times 7 means 28 minus 28. That's 0. No solution. No solution. Just because two rows are proportional. So if the rows are proportional, there will be no solution, because again, it means that one of the rows is not needed. And if one of the rows is not needed, we actually get the situation when we have two variables and one equation. It means that there will be endless number of solutions. Yeah. Because here we can actually, if we just have this equation only, it means that we can put any number instead of x, and then we can find for any x number, we can find the number y, which will then complete this equation. Yeah, that's why we need to calculate the determinant and say that if n is 0, determinant is 0, no solutions, or maybe I could say simply no solutions. Would be correct. No solutions. And we close the program. Otherwise, if the determinant is not 0, then we can actually proceed with the further calculations. So first of all, we calculate. We can usually call it let's say day x, and it means that instead of determinant, so it simply means that instead of the x column, we place C1 and C2. So this would mean that we have C1. Actually, that would be C1 instead of A. C1 instead of A1, 2, and instead of A2, 1. oh no, hold on, A11 and A21. This one. So dx, and the same for dy. So then instead of the second column, replace the, oh no, hold on. Instead of the second column, we place, yeah, that will be C1. Okay. And and yeah, so then we can print the solution. Oh, maybe let's calculate the solution. So the x would be then dx divided by determinant, and y will be the dy termed by determinant, divided by determinant. So then we can say solution, let's say new line, x equals, can we add it from here, and y equals the number calculated here. So let's take a look on the example from the home task. Let's take a look from the example from the home task, the first home task, and not the home task about the algorithms. So let me open it and let's see what was the algorithm, not the algorithm, what was the equation there. So there we had this equation. So the solution is quite simple. We can simply multiply, in this case, 2x will be 16, so it means that x is 8. Yeah, and if x is 8, that means that y is 2. So let's then try. And in this case, we can see that a11 is 1, then a12 is also 1, then a21 is 1, and a22 is minus 1. And so here we see the coefficient is minus 1. So let's try, let's compile and try linear equation solver. Yeah, sorry, that was moment. Oh yeah, here I have integer, sorry, that's my fault. We have double, of course. Have double. Sorry. Let's try again. Please be careful to write the term, and yeah, also missing modifier. Okay, that will, yeah, I'm sorry, I forgot this modifier. Need to enter it here. Sure. Yeah, in this case, I can also use the returning parameter. So if you want, you can also use out parameter. But in this case, maybe I prefer using ref. That's just such C approach. So over CS. Okay, we have, oh no, sorry, linear equation solver. That's CS. Okay, so also, okay, yeah, that was awesome. Wondering about, I need to initialize them, but okay, let's initialize them with zeros. Just just to escape this error. So let's check now. Paste it and then execute. So the parameter a1 will be 1, then a2 will be 1, then 1 and -1. And here we have 10 and 6. 10 and 6. Yeah, so we can see we got the solution. Yeah. So yeah, that was just the example of how could you basically create the logic for that practical assignment for all the linear equations if there are two variables. And in theory, we can also adjust this equation to more than two variables, but that would be maybe more complicated thing to do, so maybe not right now. Okay, do you have any questions about this linear equation solver algorithm? So again, that's a little bit of theory here. Just so don't worry, we'll have more practical things soon, very soon. Okay, then if not, we can take a quick look on the time consumption for the algorithms. Yeah, basically how to check time consumption. So usually when we have the cycle, then we can determine time consumption. In this case, we don't really need to think about. Oh yeah, maybe yeah, the time consumption for such check is basically undetermined because we don't have fixed value. So in theory, this can be endless. Yeah, so because in theory, the user can endlessly provide incorrect values, and in this case, the algorithm will be infinite. So that's why for this case, we cannot really determine the time consumption. How many time do we need to spend here? That can be endless. But yeah, so if we take a quick look on the previous algorithms we had so for example the arrays. So most we take a look on the loops. So in this case we have one loop, so the time is big O from length. We say big O from n. So that's the linear time. Yeah, if we have a simple loop, that's the linear time. If we have a loop, the one with the length, with this length inside the loop with such length, then where did we have such example? I guess that was here now. Okay, not here. But yeah, the idea is if we have loop inside loop, and both loops have the same number of iterations, then we simply need to multiply the complexity at the time, because again we have loop which has n iterations, then we have n iterations for n iterations. Of course, it gives us n power of 2 iterations. Same if we have one more inner loop, then the number of iterations will be n power of 3 and so on. If we have loop inside loop, so we have inner loops, then the time will be multiplied. So, and in this case, of course, if we have more inner loops, then then from the time perspective, it takes much more time than if you just simply have one linear loop. If you have some constant operations, then we usually don't take them into account, but sometimes, of course, they may have impact. But for large n numbers, they do not make any impact because these are large n numbers, and they simply overflow all the constant values. So for large numbers, we don't care about constants. Yeah. So then we, for logarithmical times mostly is when we have some kind of divisions in operations, and like in this case, since we have the division by 2 operation, so here we have n divided by 2 operations, then we have again, like in a general case, we're going to have again n divided by 2, then n divided by 4, n divided by 8 operations. So in this case, that's the logarithmical time. And when we divide something each time by 2, then that would be logarithmical time. Yeah, also if we divide by 3, that will also be logarithmical time. That's why we say this. Okay, and then the last thing I had an agenda for today is the practical task for. Okay, we have 10 minutes left. We definitely won't be able to go through it. So then okay, then I guess then we can take a look on it tomorrow, but we will not implement it. I will just simply explain you, and then also we'll take a look on the time consumption, and then we will move to the strings, then to the object-oriented programming, because again, yeah, for you this theory may look complicated. I understand, and that's this is not the part of the goals of our course. Yeah, so that's, I mean, this topic what I talked about today is theory, and just in case in maybe also near future you hear something about big O notation, about the time complexity, so you can at least recall something for you, and so just have at least a little bit of base to then start working with it. Yeah, but I mean, nothing what you should definitely know right now. Just if you know, then it's good. If you don't know, then that's fine. In future, you will you will learn it, and then will understand it better once you get in touch with more data. You need to process the data. You need to construct the lists, the tables, again, yeah, mostly the list tables. So then when you need to work with them, you need to find the better approach for your algorithms. But yeah, that's the talk about the future. For now, that's great that if you understand at least a little bit of this, then it's already good. Okay, then tomorrow we will have a quick look on the sorting algorithms, and after that we will start with strings, and next week we will go to the object-oriented programming finally. Yeah. Okay, then I guess for today that's it. So thank you for your attention, and then meet you all tomorrow. Bye.